My name's Andrew Colombi. I'm the CTO at Tonic, and I'm here to talk to you about the future of fake data. And if the last couple of years, months really, are anything to go by, I think the future of fake data is quite bright and exciting. If you just look at recent developments, for example, 𝗕𝗏𝗏, which is a project by OpenAI for synthesizing images, and you give it the prompt, an oil painting of a man surfing big waves made of flame, it will come up with something like this, automatically generated image from a text prompt. And that's incredible, absolutely incredible. You know, 2 years ago, if you had said, is this possible? Unless you were in the know, you would say, no way. And today we have it. And it's not just 𝗕𝗏𝗏. There's also this project called Stable Diffusion by 𝘕𝗏𝘚𝗏. And here I prompted it with dancing bears around a campfire oil painting. And again, just, knocks it out of the park. Just absolutely incredible. And it's not just images, right? It's also text. If I give this prompt, write a poem about fake data in iambic pentameter to GPT, also by OpenAI, it gave me this as a response. In a world of data, both real and fake, it's hard to know what information to take. Is it the truth we seek or the fake? I mean, that's incredible. And it might not be iambic pentameter, but it's still pretty damn impressive. Now, what makes all of these so incredible is that they are conditioned on user input. We direct the model with our prompt, and it creates something based on that, which means that it has application in commercial settings, right? This is what enables it to be useful in a business context. If it was just generating random images without any input, that wouldn't be as useful. So this is the future of fake data. Users are able to specify a description of what they need, and then the system automatically creates it from there. But I, at Tonic, don't work in unstructured data. All these examples are unstructured data. I work in structured data, tables, rows, columns, databases. So what happens when we ask a machine to fake structured data? For example, make me a database with one user that buys Beanie Babies. What's going to happen? Well, don't hold your breath, because the technology for this doesn't quite exist yet. And that's what the remainder of this talk is about. Why is it so hard to create structured data from a text prompt like you can for unstructured data? And then number two, a beginning to some sort of solution to this, a guidance on how we might solve it. But before we go to the how we might solve it, let's talk about why is it so hard. So to start with, let's define fake data. What does it mean to create fake data? And I'm going to give like a pretty abstract mathy perspective, and then we're going to dive into some more concrete examples. So to begin with, let's give our definition of fake data. Fake data is imagining new elements of a set based on a known subset. So let's pick an image for that. I like images. I hope you all like images too. Here is a space. It's an empty space. This space is a set. It can be a set of anything, but let's say it represents people's medical histories. And every dot in here is a complete medical history, right? It represents every doctor visit, every medicine prescribed, every diagnosis given. If I circle one of these examples, this example might represent a middle-aged man who broke his arm when he was a child, visits the dermatologist every year to get his skin checked, otherwise is healthy. And this dot represents every visit, every medicine, every x-ray, every single thing that paints their entire medical history. And there's going to be a distribution in this space. There are going to be some areas where the dots are more dense. These represent common medical histories, people who lived average lives, at least medically, let's say. And then there are going to be lower density regions with less common histories, people with rare conditions or data errors. For example, someone maybe that dies before they catch the flu. So like their diagnosis for the flu comes after their death. Something like that doesn't make sense. Obviously they're dead, they can't have the flu now, but it could represent a data error or something like that that's in the system. And when we create fake data, we add new elements to this space that are imagined. These pink or purplish elements, dots here, these are the new elements that we imagine from the existing data. And you're going to have more dense regions. Again, you want to have your fake imagined medical histories be more concentrated where there are more common health histories in the real data. And you also want to have those uncommon ones too, just less frequently, to represent rare conditions and also represent data errors. Like, after all, if you have data errors in the real data, your fake data, especially if you're doing things like software validation, should also contain those data errors because they may represent interesting test cases in your, for your application to do. And, a little bit of background on Tonic, if you're not familiar with us, we specialize in creating fake data for test and development use cases. We also use our data in other examples, like for sales demos and other things like that. But test and development is where I spend most of my time thinking. Okay, so that's what I mean by creating fake data. And this is what I meant by imagine new elements of a set from a known subset. And I want you to keep this image in your head as we switch gears from this sort of theoretical, abstract perspective that you might expect in like a maths class in like college, and take it to a much more practical perspective, looking at this from the perspective of a database. So here's a database. It's a very simple database. It has 4 tables, and these tables have foreign keys that are represented by the arrows. And we've got a visits table, patients, doctors, and clinics, each of these tables. And I can look at one visit here, this dark purple visit, and it has a patient associated with it, one doctor, one clinic. I can look at another visit. This is a different visit from a different patient, different doctor, different clinic. I can also look at it from the perspective of a patient. And so now when I look at it from one patient at a time, you start to see a story in the data. This patient, for example, visits a few doctors. There's one doctor here that they visited just once. Maybe that's a time when they went to a specialist for a particular thing. And then this doctor right here might be their family doctor. And then later they switch clinics and they go to a different family doctor, let's say. So there's a story here, though. There's like a real, there's something, that life created in this data. And that's what I mean by the entire history is represented in a single dot in this space. It's this entire data set here of the patient visiting different doctors at different clinics for different things. Now, we can also look at this data not from the patient's perspective, but from a doctor's perspective. This doctor here sees a few patients very repeatedly at a few different clinics. Maybe they're a family care doctor or a primary care doctor, and they see the same families, the same people over and over again. And they might work out of different clinics at different times of the week, for example. And this doctor here, another doctor, they see patients just once and then that's it. Maybe they're emergency doctors and you don't have many emergencies, so you don't see the same doctor over and over again in an emergency care situation. And they work at a single hospital, for example. So these are very different stories told from the perspective of different doctors in this data set. Now imagine synthesizing this data. So not only must we synthesize the complexities of a single patient's history, we must also weave into that the complexities of a doctor's specialization and multiple doctors' specializations. And that's why this becomes so complex. And we can really kind of define that complexity by looking at this from the perspective of a graph. Now, I don't know how computer sciencey and how mathy this audience is, but in computer science, when we refer to a graph, what we're talking about is a web of connected things. And so if I just drop away the tables, I just basically took away the outlines of these squares or rectangles that are the tables, and I have this web of connected things. And each of these formerly rows of a table are going to be nodes in the graph. And then these foreign keys that represented the patient's visit or the visit's doctor, et cetera, those are going to be called edges in the graph. So we've got the nodes, these purplish lines, and we've got the black edges that are defining the foreign keys. So this is a graph in computer science, and graphs have two big problems. The first one is that they are very high dimensional, and the second is that they are very sparse. So what does that mean? What does high dimensional data mean? People often talk about high dimensional data. I think it's very in vogue, especially with lots of data science applications happening today. And people say, oh, that's a very high dimensional problem. Well, what do they mean when they say it's a high dimensional problem? Don't worry, I'm going to tell you. So here's another perspective on a graph. This perspective is what computer scientists call an adjacency matrix. And it's a way of representing this web in the form of a matrix. And so a matrix here has rows and columns. Each row and each column represent nodes in the graph. So I have V1 here. You'll see that's a column. And, whoops, went forward there. It's a column and it's a row. And in fact, each edge, so each connection, each patient taking a visit, is represented by a 1 in the appropriate row and column of the adjacency matrix. So for example, this patient going to this visit is represented by a 1 right here in the adjacency matrix. And so every one of these connections here is represented by a 1 in this adjacency matrix. And that's where the dimensionality comes in. If you think about just sort of like, well, how many numbers would I need to represent a graph in this adjacency matrix? Well, each node gets a row and a column, and for each node, there's going to be a number squared in the number of nodes, meaning that if the total number of numbers in this matrix is squared the number of nodes in the graph. So that in computer science, we say that's a problem that grows n squared. What that means in practice is that for each of these entries in our database, going back to thinking about these as entries in a table, we are growing at a number n squared to that. So if we have 1,000,000 rows in our database, this matrix has 1 trillion dimensions. And 1,000,000 rows in a database is like nothing for a database, right? It's very common for databases to have billions of rows, and I don't even know what number it is that when you square a billion. It's a very big number, and it's certainly much higher than the number that a computer can deal with when solving these graph problems and trying to solve, data synthesis problems. So going back to our original kind of theoretical perspective, this circle, or this dot right here that I'm circling, represents an entire portion of this adjacency matrix. And that's why it's a high dimensional problem. This is where the trillions of dimensions, or more than trillions of dimensions, come into play when people talk about synthetic data and the high dimensionality of structured data. This is a difficulty for computers. They are not good at very high dimensional problems. And I think this is probably, there's like 2 slides in this presentation that I think are the most important, or maybe the most interesting. And I think this is one of them, maybe not with the guy with the exploding head, but the one before it, because I think frequently people talk about the high dimensionality of data science problems, and it's useful to have in the back of your head, well, where is this high dimensionality actually coming from? And this is one way of explaining that through the process of building an adjacency matrix and understanding the size of that adjacency matrix. Okay, so let's get back on track. What comes with high dimensional spaces is another property called sparsity. So what does sparsity mean? Sparsity means that when you have these really high dimensional spaces, the points in them, like the individual elements within the space, become very rare and very far apart. And that makes it even harder for a computer to extract a pattern from essentially what is a vast emptiness when you have these very high dimensional spaces. And these two things, this high dimensionality with sparse data, is commonly called the curse of dimensionality in mathematics. It's such a common problem that it has its own name, the curse of dimensionality. Now, the curse of dimensionality is one problem in faking structured data. It is not the only problem in faking structured data. It is the only problem I'm going to talk about in depth in this talk, but I wanted to highlight some of the other challenges that we also have when dealing with faking structured data, simply because they're actually, equally important, but we don't have time to talk about everything today. So what else is there that makes this a problem? There is no common public data set to experiment with, right? If I want to work with images and make a model that creates images, there are research grade data sets out there that are freely available in the public that I can download and I can use to train my model. And this is, equally important as the curse of dimensionality for people like myself that are, we're trying to push the envelope of what's capable here, but it's very difficult to get access to data. And that is why it's so important for us to partner with folks like you to get access to these challenging problems that organizations around the world face. So that's one additional problem. The other one here is there's no agreed upon format for structured data. In unstructured data, like images, for example, everyone agrees. There's a grid. Each grid has 3 colors, 3 channels. There's 1 byte for every channel, R, G, and B. And that's it. That's how we represent an image. Everyone agrees. Text is the same. There's a few encodings for text. UTF-8 is basically the one that everyone uses now. And that's all you need to do. Whereas with databases, there's no agreed upon format. Even CSV is like, I don't know if anyone's worked with CSVs directly, that is not agreed upon format. That is a difficult format to work with at times. Okay, so let's get back to the curse of dimensionality. I wanted to mention those, but we're going to spend the rest of this talk sticking to the math and not so much the policy problems. Right. So part of the challenge of a high dimensional space is, that this data, part of the challenge of this data is that it lives in such a high dimensional space, right? This adjacency matrix with all these dimensions, et cetera. But is it as high a dimension as I claim it to be? Well, let's make a simplifying assumption. Let's just assume for a moment that doctors only work out of one office. They work out of one clinic only. So if you knew which doctor you visited, you would automatically know what clinic you also visited because they only ever work out of one clinic. What this would mean in practice with my adjacency matrix is I can eliminate an entire set of nodes from my graph and therefore an entire set of rows and columns from my adjacency matrix. This means that I've effectively reduced the dimensionality of this space. And I've reduced it from a space of like all possible configurations where doctors are visiting multiple clinics, which we agree is not possible in this new kind of simplification, to a space of plausible graphs, right? The plausible graphs are slightly smaller because we know that doctors only work out of one clinic. So let me give a much simpler example to kind of drive this point home. Suppose I tasked you with picking points in the universe where human beings live. Well, you could say, okay, well, the universe is 3-dimensional, string theory aside, and therefore I'm just going to pick random spots in the universe, and that's where my humans will be. But we all know that's not very plausible, right? Humans all exist on the surface of the Earth. So if I can just pick from places on the Earth, that will make my life easier. And in fact, we can pick random spots by saying, let's pick longitudes and latitudes on Earth. And this effectively reduces the dimensionality of my sampling space because longitude and latitude are only 2 dimensions. They're 2 numbers to represent any point on the Earth. And this idea of being able to just sample on a smaller dimensional surface, the sphere is a 2-dimensional surface because it can be represented by just 2 numbers, applies even in this more complicated sort of abstract space. We can still think about a surface within that, which we call the embedding space. And that embedding space exists in the ambient space. The ambient space is the higher dimensional space. So ambient space is the universe. Embedding space is the surface of the Earth. Okay, great. So if you buy that, I can reduce the dimensionality from all possible configurations of medical histories to plausible configurations of medical histories. Plausible meaning, people don't visit a new doctor every time they go to a doctor, or doctors don't work out of a million different clinics, but they work out of a subset of clinics, etc. How am I going to do that? Well, before we get to that, I think now is a good opportunity to take a pause and just restate the overall problem that we have for creating synthetic data. Step number one, we'll compute the lower dimensional space of plausible elements. That's what I've just been talking about, right? Let's compute this lower dimensional space of plausible elements. After that, we need to sample from the space of plausible elements. And after that, we need to conditionally sample based on user prompt, right? That's what I promised you the future of fake data was, working based off of a user prompt. So let's start with dimensionality reduction. Dimensionality reduction is a very well-researched field. We talked about the curse of dimensionality having its own name because mathematicians run into it so frequently. Well, they have equally frequently attempted to reduce the dimensionality of these high dimensional spaces and come up with a myriad of mechanisms to do so. And the one we're going to use today is called a variational autoencoder. And the variational autoencoder we're going to pick in part because it is actually what stable diffusion uses at 𝗕𝗿𝘀𝗏𝗏 to create this image of the bears dancing around the fire. They also had a problem with dimensionality, right? They have these, let's say, 1,000 pixel by 1,000 pixel images, and each pixel has 3 channels, like we discussed earlier. So that's 3 million dimensions. I mean, 3 million is nowhere near trillions and trillions and trillions like we have in our structured problem, but it's still a lot for a computer. So they, one of their key insights was, hey, can we use a variational autoencoder to reduce the dimensionality of the space? So we're going to follow their example and use a variational autoencoder. How does a variational autoencoder work? What does a variational autoencoder do? Great questions. Here is the basics of a variational autoencoder in 5 minutes or less. A variational autoencoder, its purpose in life is to repeat the input into its output. So we call this side the input. It is known as the input vector. Each one of these little squares is a dimension input vector, and it tries to repeat whatever is presented to itself on the input vector. It's a neural network. It does lots of matrix math and the power of GPUs. And at the other end of it, hopefully, if everything is going well, the output vector will look exactly like the input vector. That's what a VAE does. That's what autoencoder means. It encodes. Auto in mathematics, they frequently use that to mean sort of like repeats onto itself or something like that. So the autoencoder repeats onto itself. How does it work? Well, I think it's useful to talk about how is it trained first. So, neural nets, they go through this training process. How does that work? Well, you take your desired input, this image of a person stepping on a soccer ball, and you're in Europe, a football ball. I don't know, that doesn't ring off the tongue quite as well for me. I'm just going to say soccer ball for now, apologies. So a soccer ball. And then after the machinations, hopefully the output is the same as the input. Well, if it's not the same, what we'll do is we'll take the difference. So we'll literally subtract the input from the output. And using that difference, we'll train. There's a process called the feedback process in the neural network. I'm not going to get into the process of how that works, but it's used, that difference is used to change the weights within the neural network to train it so that the next iteration it can be slightly better. Okay, so that's how it trains. Now, how does it work? What are the main components? The key to what makes a variational autoencoder work is this latent vector. The input vector is where we put the input, and then what the encoder does is it essentially squeezes down the dimensionality of the input vector into this lower dimensional latent vector. Why do I say it's lower dimensional? Well, it has fewer squares, right? This is all the different numbers that represent the input vector, and the latent vector just has fewer of them. So therefore, it is lower dimensional. And we know that the latent vector is able to capture the essence of whatever the input was, because through the magic of the decoder and GPUs and matrix math, we're able to somehow recover what the input was. That's the whole purpose of this autoencoder, right? Is to take the input and reproduce it on the output. So this latent vector is able to capture essentially the essence of what the input was. So that's kind of really where the power of the autoencoder lives. And if you like analogies, it's kind of like saying the phrase crayon drawing of a white poodle in a grass field can, in 50 characters, describe an image of 1,000,000 pixels. 50 characters is 50 bytes, so you might say 50 dimensions, let's say. And this is, as we discussed, 1,000,000 pixels would be 3,000,000 dimensions. So that's kind of, you know, as an analogy, what you might think this latent vector is able to do. Another way to think about it is the latent vector is this lower dimensional space. It's our sphere that represents the Earth in the longitude and latitude case. The latent vector itself is the longitude and latitude, and the input vector would be 3 dimensions of any spot in the universe. So this is, you know, this is the latent vector, and this is what essentially creates these lower dimensional spaces. Now we have a lower dimensional space. We have our lower dimensional space. It's called the latent vector. How do we sample from it? Right? That's step 2, sampling plausible elements. Well, to sample with a VAE, what you do is you surgically remove the encoder. And by removing that input space and using this latent vector now as your input, you're effectively picking points in the plausible space, right? The latent vector represents the plausible inputs, or the plausible spaces, the plausible outputs, I should say, rather, in this lower dimensional space. And if I pick just random noise and I fill it into this latent vector, on the other end, I'm going to get an image that is like the images I trained on. Now, just imagine, for the sake of argument, that we trained on images of people stepping on soccer balls. This would be another possible output based on my latent vector. And if I switch up the input by, you know, changing the values, we're going to get another image of a person stepping on a soccer ball. So that's kind of how we effectively pick values in this lower space. But that's not all I promised. I promised one more thing: conditionally sampling plausible elements, right, based on user input. Well, for this one, I only have a few minutes left, so I'm not going to give away the complete future of fake data. Instead, I'm going to leave you with rather than leaving with a solution, I'm going to leave you with a problem. You know, problems are kind of more interesting than solutions anyway, and that's kind of my second most important slide, is this idea that the problem is more interesting than the solution, because in a few years, these solutions, that whatever I spout right now, are going to be obsolete, and there's going to be new problem or new solutions to the problem on the horizon. Let's go back to our problem, though. Our problem was we wanted to create these medical histories. So if we look at our database, here's a typical patient's medical history. And what I said is I want to synthesize conditionally. What does it mean to conditionally synthesize? Well, so far, I've just been picking random points in my plausible space. What I'd like to do is be able to guide that. So let's say I want to guide it by saying, give me a patient that is a male and 42 years old. Essentially, what I'm doing is I'm kind of pinning certain parts of this really high dimensional space, all the different inputs, and I'm saying these specific spots I want to specify. I want to specify the gender of the person, and I want to specify their age. And from then, let the machine fill out the rest. What are the visits? What are the doctors? What do the clinics look like? So how can I do that? Well, there right now, we're not directing the system at all. We're just picking random latent vectors, and those random latent vectors create these random histories. But what if we could, what could we do to like actually guide the system a little bit more? There are two possible ideas. The first idea is, what if we can pick our latent vector more intelligently? So rather than picking a random latent vector, we can somehow pick a latent vector that represents a 42-year-old male right from the get. And if we can do that, then let the system do the rest. The challenge, of course, here is understanding these latent vectors is really complicated in a research project onto itself. Maybe a hopeless task, I don't know. The latent vectors themselves are very opaque. They're like the machine's understanding of how to condense an idea, or condense a spot in this very high dimensional space. So that's a difficult challenge. The other possibility is that we could bias the decoder. So we could have a latent vector as usual, but then have some sort of side input that specified that we want a man that's 42 years old. And in doing so, bias the decoder to take this latent vector plus that input to give me an output that's relevant. So at this point, we're at like slide 67 or so, and we have just a few more left. So good job getting through those. I'm just going to say 3 more things before we wrap up and go to questions. First, the future of fake data is conditional. We've already seen that in the unstructured data case, and the results are really incredible. I mean, here's ~DALL-E, Stable Diffusion, GPT, and since I created these slides, they've already iterated and created even more impressive algorithms and approaches. But we don't have anything yet for the structured data set. The structured data synthesis problem is really challenging. There's the cursor dimensionality, which we just spent the last 30 minutes talking about, but there are also these other policy problems that are equally important. No common public data set, no agreed upon format for structured data. And there are solutions out there yet to be discovered. Here's one solution, but it's just a sketch of a solution. We do have this at Tonic and we do use it. But yeah, this is kind of the entirety of what I have to share today. And at this point, I will go to questions.
Thank you so much, Andrew.
Yeah.
Really interesting. Are there any questions from the audience?
Yeah, I do. I just trying to wrap my head around it. From the perspective of Tonic and the solution that you guys have, you obviously walk onto those boundaries right now, but is it the things that you just explained, does it resemble what you guys actually do, like in the back end of things of Tonic.ai, or is that a simpler version of that, because it's still hard to get that right, because all you get in Tonic is basically structured data, right? It comes straight out of other databases, so that you synthesize in that.
Yeah. So we do have so I don't know how familiar you are with Tonic, but there's a concept in Tonic of a generator, and a generator is responsible for creating fake data. And the generator trains on existing data before it generates more fake data. And we have kind of a sliver of what I described. We do it for, we use the kind of the exact approach that I described for columns in a table, but we haven't yet done it across tables, this exact approach. We have other mechanisms for dealing with cross table that aren't neural network based and variational autoencoder based. But yeah, we for variational autoencoder and that kind of thing, we do have one. If you use our product, it's called the AI synthesizer, and you can select it as you're playing around in the UI.
Right, nice, thanks.
Thanks.
Yeah.
Any other questions in the audience?
Oh, I have a bonus slide, I think. What's my bonus slide? Oh yeah, I tried this in ChatGPT. Something like the iPad with, yeah, I tried it. I told it to make a database, and it didn't do so well. There we go.
Great. So if there's no additional questions, I really want to thank you, Andrew, for giving us this explanation. And yeah, it was really interesting.
All right.
Thank you. Bye-bye.
Bye bye. Thanks, Andrew. Bye.